All right, this is chapter 2, section 2.1, uh, linear motion. Basically, motion in a straight line. Okay, we're not at 2D motion yet, but Pikachu, imagine Pikachu moving in a straight line. Okay, he could also be moving up or down. Maybe he goes up in the air and he falls back down. Okay, 1D motion, Pikachu falls out of the sky. It's 1D. He's moving downwards. Okay. Chapter 2. Okay, we're going to talk about acceleration. We're going to talk about velocity, things falling out of the sky, hopefully nothing hitting you. Okay, so yes, motion in one dimension. Now, I strongly recommend you clicking on these PhET simulations. They're really, really useful. They'll give you some practical experience. Yes, I like Pokemon, and I apologize for calling Charmander Charizard. I don't know. It's okay. I've reviewed my Pokemon now, and it shan't happen again, I dare say. All right, well, let's get started. Gotta get out my stuff. Okay, gonna be drawing some pictures as usual. Okay. I will be moving back the homework a day, and I'm probably going to delete one assignment from the class. Maybe take out a chapter. Okay, I don't know what that was. Anyways, let's keep going. All right, so we're gonna talk about linear motion. It could be a horse running, maybe the horse is speeding up or slowing down, but it's moving in a straight line. Okay, you can have uniform motion where the velocity is constant, so there's no acceleration. Okay, so that would be uniform motion. Or you could have acceleration. Here's my cheetah. He's going really fast. Cheetahs can basically get to 70 miles per hour in 3 steps. So it's a tremendous amount of acceleration. Okay, but there's actually only so much acceleration the human body can take. So astronauts, we can't make them accelerate too fast because it can kill the astronauts. If you saw the Hail Mary project, that was a great movie because it was very realistic in the sense that it takes a very long time to slow down. So if you haven't seen the Hail Mary project yet, actually you should read the book, but you should go see the movie. The book, there's lots of physics. They took out a lot of the physics in the movie, I'm not gonna lie, because they thought normal people, they won't get it. It was too hard. Which was actually like the main reason why I liked it because it had so many cool physics in it. Actually, in the calculations in the book are very accurate. So if you follow along in the book, he does a lot of calculations to figure out like, hey, what's going on here? And they're actually real. Okay, so the calculations in the book are real. All right, I got my paper out here. Let's go. Okay, so when you accelerate, you have to slow down or speed up not too quickly because that would create a large force. Remember, if there's an acceleration, that means force. Okay, and and that means basically we're going to talk about. Let me just write down Newton's second law. Hopefully you may have seen it before. If you have high school physics. If you haven't, that's okay. It's gonna be one of our main equations. This is Newton's second law, and it simply states that force equals mass times acceleration. Okay, this means that it means a lot of things. We're going to talk about this in very detail throughout the semester. Okay, but if you have a force, if there's an acceleration, that means that there was a force. There we go. Need a little bit more light to focus, maybe. Right. So if there is acceleration, then there must have been a force. Something was causing it to move. I don't know why my camera isn't focusing. There we go. Okay. So if you have an acceleration, that means if your velocity is changing, then there's a force. Something is causing your velocity to change, and so there's a force acting on it. Okay. And so we say that acceleration is equal to delta V delta T, basically. If for some reason your velocity changed, then there was an acceleration. We talk about the rate of change of your velocity. How quickly did your velocity change? If it changed very quickly, that must have been a big force, okay? And so we could also write this another way. We could say VF minus VI. So what was your initial velocity? And what was the time it took you to do this? So TF minus TI, right? How quickly did your velocity change? And that tells you how much did you accelerate. Okay, we'll talk about this later. But acceleration is a big deal, and we're going to talk about it a lot. And this is Newton's second law. Yes, Newton's second law. Okay. Newton was a famous physicist, of course, in the 1700s. He basically put down everything that we know about classical physics. He was the really kind of the father of modern science, okay? And so we'll spend a lot of time talking about Newton's laws, but that's a big one, okay? So when a diver jumps, his motion is he's falling down because of gravity, and we call this free fall. So if you're just falling, right, then you're in free fall. Okay, so there's Pikachu. Okay, he's up here, and I'm gonna let him go. He was in free fall. For that one moment, Pikachu was weightless. Yes. Okay, so Pikachu is in free fall because gravity is always pulling you down. You're always accelerating. It's just the floor is underneath you, so you're not moving. Okay. Now people talk about gravity as a force. Is it a force? Or is it really the curvature of space and time? It's it's hard to say. It's really kind of not a force because if it was a force, that implies something was touching or something was pushing it. Okay. We don't know if there's a particle that causes gravity. We think that it's more like matter is bending space. Yes, it's like a giant trampoline. When you put something heavy on it, it bends space. Okay. And there's more weirdness than that because, if you accelerate quickly, it basically is the same thing as like gravity. So if you're in a car and there's acceleration, that's basically like gravity is happening. You experience this acceleration. Your car has a certain amount of force the motor can apply. And so if we go back to these dots here, then the distance between our dots becomes greater and greater each second. And so our car is accelerating. Okay. Bicycles moving to the left with increasing speed, which is the following motion diagrams illustrates this motion. Well, not the ones pointing to the right. Not those ones because we said it's going to the left. Okay, so there's only two going to the left, and it says it's increasing. Okay, well, D here, it's going fast, and then the spaces get less and less. That means it's slowing down. It can only be B. Okay, it's going to the left, and it's speeding up. Okay, I would strongly recommend reading the chapter. Okay, go through the PowerPoints. You can follow along with my lectures, but go through the chapter. Read it. Reading is good. Someone said After was the can I do something else besides reading the book? I'm not a literate person. Like, bro, you have to read books. Okay, there's a funny TikTok. This guy, he did a TikTok. He kind of says some bad words, although I think you're adults, so maybe I'll post it anyways. But he's like, I read books so you don't have to. No, that's wrong. You have to read the book. Okay? Because reading the book makes you smarter. Pikachu wants you to read the book. So read the book. Okay. Where are you gonna sit, Pikachu? Okay. You're gonna sit over there. Yeah, okay. He says he's good there. Okay, reading questions. The slope at a point on a position versus time graph of an object is the. Okay, wait, I don't know what it said. The slope at a point on a position versus time graph of an object is what? The object's speed at that point, the object's average velocity at that point, the object's instantaneous velocity at that point, object's acceleration at that point, distance traveled by the object. Okay, so it says the slope at a point on a position versus time graph is what? Okay, well you know what? I hope you read the book, but I'm afraid that you haven't. So let's draw a picture. Let's make a position versus time graph. Useful to draw. I've got some graph paper here. It makes me sad because it's not in centimeters, but yeah, whatever. Okay, so we're gonna have position versus time. So time is going to be down here on our axis. See, I'm putting the time there. That says that it is in seconds. Okay, and we're gonna have increments here of what this spiffy graph paper. If you don't have graph paper, you should get some. You can order some on Amazon and different colors. I would get pink or purple, maybe yellow like Pikachu. So here's our origin. This is going to be 0, then 1, 2, and the units are over here, so I don't need to write seconds on each one because that's super annoying. Okay, I'm trying to make your life easier. I'm writing the numbers here. Oh, this is 12, 13, 14. Okay, and then over here, we'll call this Z just because we don't want to get too comfortable with X. Okay, it could be X, Y, or Z, and this is going to be in meters. Okay, and this will be 1, 2, 3, 4, 5, 6, 7, 6, 6, 7, 9, 10, 8, 9, 10. Okay, so let's say that our object is moving at 1 meter per second. Okay, so at 1 second, okay, at 0, he starts here. It's going to move at 1 meter per second. After 1 second, he's going to be here. After 2 seconds, he will be at 2 meters and 2 seconds. Okay, and then at three seconds, that's down here, he's going to be at 3 meters, and so on, thusly. And we can, if I had a ruler, I don't know why I don't have a ruler. Why don't I have a ruler? You know what? It doesn't matter. It doesn't matter. I can use this prism because I'm cool like that. I'm just going to draw it this way. Okay, that's fine. The light is coming from over here. I can continue this line here, right, with my prism, okay? And it basically tells us that at every second it will have gone 1 more meter. Okay, and what does the slope of this line tell us? Well, we hopefully maybe you remember, okay, but velocity, okay, if you think about speed, right? Speed has, I'm gonna draw these square units here. In our normal everyday American lives, we think of miles per hour. This is wrong. Okay. You want to think in meters per second. Okay, that's speed. That's also the units of velocity. Okay, it's meters per second. Okay, so the units are telling us that velocity has meters per second. Okay, and so if I look at the slope of my line, okay, what is the slope of the line? What's velocity? Okay, so if I want to calculate the velocity of my line here, okay, I'm going to take two positions anywhere on my plot. Okay, it doesn't matter where they are. I'm going to say, let's go with this one right here, and then we'll go with this one right here. And so to calculate my velocity, I'm going to say my velocity is the x final position minus my x initial position, okay, divided by my final time minus my initial time. Okay, and you want to do final first before initial because that's really important. Okay, because the sign is going to tell you what direction it's moving. Okay, so let me say that again. You want to put the final position first and subtract the initial position because the sign will tell you what direction it's moving. That's really important. So let's look at our plot here. Okay, up here at this plot, we've got our coordinate system here. The first one is going to be time, so that'll be we're at 5 seconds and 5 meters. Okay, so see what I did there? This is my the first one. So this one is seconds and this is position. Okay. Down here, this one our time is 2 and our position is 2. Okay, so let's put it in here then. So our average, and this is average velocity. Okay, we're doing average velocity. That's our average velocity. Okay. And average velocity, we don't really know what happened between the final position and the initial position. I mean, we know where it was at those two positions in time, but we don't know what it was doing, right? It could have been going like that. We don't care. Okay, this is the average velocity. We don't care what happened. We just know these 2 points. We're going to find the average velocity. It's fine. So my final position was 5. My initial position was 2. Okay, my final time was 5, and my initial time was 2. Well, this gives me here 3 over 3, or 1. And then my units, of course, are meters over seconds. Okay, those I should have those in there. Meters over seconds. So meters over seconds. So now we got our velocity. This is 1 meter per second. That's our velocity. How many miles per hour is it? Oh, you should know it's 2.2. Yeah, it's 2.2 miles per hour. Let me go back in my notes. Oh, where's my? I wrote it down in big letters. I know I did. Oh, there it is. Oh, there it is. Okay, well, 1 meter per second is 2 miles per hour. That's fine. It's actually 2.2 miles per hour, but whatever. Okay, so it's two miles per hour. Okay, we found our velocity. Now, what if the slope changes? What if we got something like this? Let's find the velocity of this fast moving Pokemon here. Which Pokemon is this? I'm going to reach into my bag of Pokemon. I think it's Jigglypuff. Is it Jigglypuff? Somebody's gonna say something if I get the wrong Pokemon. What does Jigglypuff look like? Oh my gosh. Yes! It was Jigglypuff. I knew it. Ha! See, somebody said I'm not good at Pokemon. Not true. I am good at Pokemon. I mean, how many how many physics professors do you know that know most of the Pokemon? Not many. Okay, not many. Jigglypuff. All right, so let's find some time here. Jigglypuff is really moving. I think he's a fast Pokemon, but actually his name suggests he's not. Okay, but let's get Jigglypuff's velocity here. All right, I see he lines up here on this one, and then I know, so I'm gonna use those 2 points because well, I don't have to. Let's use one in the middle here. Okay, so this coordinate it's a 7.5 right there. That's 7.5, and then it's right in the middle. And we'll say its time is 2.5. So it's 2.5 and 7.5. Oh, yes. Okay, and then this spot right here, what are the coordinates of this? This is 3. No, it's 1 goes first. 1 and 3. Okay, so my final is the time is first, it's position, so it's 7.5. and this is velocity of Jiggy. Yeah, it's my Jigglypuff. Okay, 7.5 minus 3. That's my final time. And then on the bottom, I'm going to have 2.5 minus 1. This is Jigglypuff's velocity that we're calculating now. Okay, and so then here I'll get this is 4.5 divided by 1.5. Okay, and now I'm going to use I can do this on my phone. It's like almost, it's close to three-ish, maybe, but let's see what we got here. Okay, 4.5 divided by 1.5. Oh, it's 3. Duh. Oh man, okay. V Jiggy, okay, is 3 meters per second. Yeah, that reminds me of a Will Smith song, Getting Jiggy with It, but maybe you haven't listened to that. Its object is its average velocity at that point. What? Instantaneous velocity at that point. Okay, that's true. The slope at a point on a position graph. Yes. If we could just find one point, that would be the instantaneous velocity. Oh, wait. I'm not sharing my screen anymore. Okay. So here's the right answer. Okay, the object is the instantaneous velocity at that point. Rating, okay, a person at rest. Actually, you know what? Let's go back. I want to talk about the difference between instantaneous velocity and average velocity because I really don't like this question. Okay. Um, I think they oversimplified the answer here. Okay, you know what? I'm gonna draw let's look at say point. So let's say we had another position versus time. Well, I guess we can use this one here. Okay, let's say that instead of a straight line, okay, our object goes something like this, and then it maybe speeds up. Okay. Our object speeds up right there, and we want to know, well, what is the velocity, say, right there? Okay, because obviously it's changing. Down here, I can just find the slope of it, okay? And that would give me my velocity there. Okay, but what about if it's constantly changing speeds here? Okay, how could I find my um how could I find my instantaneous velocity at that point? Well, that's a really good question. Well, what you would do is you take a straight line here and you go like this and you draw a tangent line, okay? A line that only touches the curve at this one point. I can't draw a good tangent line because my pen is too thick here. And then what I would do is I could calculate the slope of this line, okay? And if I calculated the slope of this line, so this is my rise here, and I've got my run. So this is my rise, and this is my run. Okay. That would tell me the instantaneous velocity at this point right here. That would be my instantaneous velocity at that point. I'd take over here. So this would be, I'd call this one x of f and t of f, and this would be xi t of I. And I could do that. I could calculate those right here. So this would be x of f minus xi, and then I'd have tf minus ti. Okay. And if let's just calculate it real quick and see what the instantaneous velocity of this thing is. Okay, so my position here is 6 and my time is 12. Okay, and over here my position is 2, so this is minus 2, and my time is 7.5. Okay, so up on the top here, um yeah, up on the top there, I would have, let's see, that'd be 4. 4 divided by, that'd be 4.5. Okay, so it would almost be 1 meter per second. And that's true. It looks like this line is almost parallel. It's not quite as steep, so it should be a little bit less than the 1 meter per second line. Okay, so 4 divided by 4.5. Okay, so that would give me a velocity of 0.8889 meters per second. Okay, so this would be V instantaneous. But I'm going to round this off. Basically, I'm going to say, all right, this is 0.9 meters per second because I only had two. If that's one significant digit, if I had two significant digits, then I would write, okay, so that, yeah, this is what I'm doing. So that's my V instantaneous velocity of that point right there. Okay, so of my tangent line to that circuit, that curve right there. Okay, so that's kind of the difference between the instantaneous velocity and the average velocity. Instantaneous velocity could be, hey, what is my velocity at this one point? And then my average velocity would be, I take two measurements over a big time period between those two, and then I say that's my average velocity there. Okay, well, I think we went through a lot of things here on this video. And so I might stop here now because let's see if this is equivalent to section 1.1. Okay, yeah, we're talking about oh man, they're going really slow. Okay, well here's a good one. All right, let's talk about this one. Okay, so here's our position versus time. We did that. This one is interesting because you see that the slope has changed. Okay, so there's several different slopes here. Okay, the first one we've got our slope here for this first part. Okay, so that's one slope. And then on the second part, we've got a different slope here. Okay. And then on the third part, okay, we have yet another slope. Okay. So whatever our particle is, okay, it's changing velocities, and you can see that down here in the bottom. Okay, so at first, it's got this kind of lower velocity, then it slows way down. The dots get really close together. That's this part in here, and then it speeds up. That's the red part in there. Okay, so that's what we were just doing. This is a nice picture. So on the problems, they're going to ask you, hey, here's this plot. What is this? What's the velocity based off of this plot? And I think you know how to do that now, so we're just going to skip through this part. Okay, and then of course, you could make this table of values, and you could plot this table if you wanted to. You could do it by hand. You should know how to basically do that by hand. Okay, so you'd basically say, okay, yeah, it looks like let's draw this table real quick, and then I think I'm gonna end this video here. This should get you through, I think, the beginning of chapter 2. Yeah, and we don't want to make any video. I'm going for short videos because oh my goodness, I don't want to listen to me talk. Okay, so we'll make a table here, and this is going to be position versus time. Okay, and the time, we'll put the time down here in seconds. Okay, and so if we look at our table, yeah, this will be, so we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so the question is, okay, what do we want to make the units on this side? I think we're going to do increments of 50 here, right? This will be 50, 100, and so on. Okay. So I'm going to look at the table here. So this is 50, 100, 100, 150, 200, 250. You can make this whatever you want. Okay. 400, you just need to make sure it covers all of your data. So 500 and 540. Okay, so we got a nice graph table here. I can add some more numbers. Okay. So now I'm going to go back and look at that table. My first point is going to be at 0, 0, so that's at the origin. Okay, my second point is going to be at 0, 60, so that's a little bit above there. The next point is going to be at time 2, and then 120, so that's about yay. And then my next point is going to be 3 at 180, which is about here. Okay, and then my next point is going to be 4 at 200. Okay, so we kind of looks like we slowed down there. Then my next point after 200 will be at 5. It's going to be at 220. Okay, so 5 at 220 is about there. And then at 6, it'll be 240. And then at 7, oh, it looks like it's speeding up. It's going to be at 340. Okay, so it goes right here. And then at 8, it's at 440. Oh man, this thing is booking now. 440 is right there. And then at 9, it's going to be at 540. 5. That should be 8. And 9 should be, yeah, 540 is actually there, and that should be over here is 540. Okay, so I recreated this plot here based off of the data in my table. Okay, so let's go back to my table. So I just took this data as a 0, 0. I drew that on my plot. Okay, and then 160, I put a the 160 is right here. It's a little above the 50. Okay, and then my next point is 380. 180, I put it there, but it's, you see, I plotted this by hand. And that's an important skill to do. I don't know if you have plotted things by hand, but it is useful. Okay, so okay. And then let's see what else we got for this one. Okay, we made a table here. All right, and we talked about this. We know how to calculate rise over run. Okay, we can do that. Okay, and we know how to read the position of an object. Let's see how much we got here. Are we going to get through all this? This is okay. 2.1. Yeah, we'll go ahead and look at some of these problems now. And oh, here's a good one. Okay. A graph of position versus time for a basketball player moving down the court appears as follows. Okay, which of the following, okay, so this is his position. So we got x over t. Okay. And if his position doesn't change, what is his velocity? Well, if his position's not changing, VF equals VI, so, or no, sorry, XF equals XI, so 0 divided by that time interval, he's not moving, he's standing still, okay? So if the slope is 0, that means his velocity is 0, okay? So right here, this first part at least, his there's no slope, so it's changing, okay? The second part here, okay, he's got a constant slope. That's really important because if we know what the slope is, that's a constant value. It doesn't change. And so if we know what that constant value is, it's the same over that whole thing. And the question is, would it be negative or positive? Well, if the slope is going down like this, it's negative. So that means our velocity has to be negative. Okay. So let's think about A here. Well, A, yeah, it's flat here, but this is a non-zero velocity, so it can't be this one. B here, the velocity is 0 at the beginning. That is correct. But then it looks like the velocity is changing. Okay. We don't have that. We have a constant velocity. The velocity doesn't change. The slope only has one value. Slope is constant. That is one number. And so that means it can only be C or D because we have one value for the slope of our line, but the slope is negative. Okay. The slope is negative, and so it has to be C. Now, what do I mean by a negative slope? Okay, let's talk about a negative slope, and then I'm going to end this video because then you can read the rest. I think we've probably done enough to get you started with chapter 2. Okay, I'm going to stop share. Go to there we go. Okay, let's draw another particle here. Okay, and we'll just make it, it's coming in here, and we'll say its slope. Let me get my prism here. This is my ruler. Oh, I don't like that. Okay, we want a negative slope. I'm gonna turn it around. You can see it. Okay, so let's say that on this one, okay, I take some measurements, and now what happens next, okay, is my particle is decreasing like this. Okay, so the velocity, the position is decreasing. It's going towards negative, and then over here, this is 13. Okay, so this has a negative slope. These other ones over here have a positive slope. Okay, I got a positive number up here when I found the velocity. When I did rise over run, that was a positive value. But now let's look at this part over here. Okay, so my final position is going to be right here, and that is going to have a time coordinate of 13, and then my y coordinate is my position, so it's going to be 300. Okay, this is my final. So this is X final and T final. My initial is up here. Okay, so my time here, my initial time was 9, and my initial position was 500. Okay, so, and let's see. Yeah, we'll have a, what do we have? We'll say this one. Okay, and what Pokemon is that? It is the Lapras. Oh, dang it. Okay, so the Lapras, okay, he dives underwater. He goes down here and he's like, "Ugh." I don't know. I think he does what he sounds like. He's like, "Ugh." He's here and then he's like, "Ugh, ugh." Okay, so he ends up here. What is his velocity? He is diving straight down underwater. Okay, so we'll say, what is the Lapras velocity as he descends into the depths of the Pokemon Sea? Okay, his final position is 300 minus his initial position, and it takes him how many seconds? 13 minus 9. Wow, the Lapras is cruising. Okay, so this is, we get minus 200, minus 200, and then 13 minus 9 is 4. Okay, so he is, yeah, 13 minus 9 is, yeah. Okay, so that is 50 meters per second. 50 meters per second. Wow, times two, he's going, oh my gosh, he's going 100 miles per hour. Oh my gosh, look at the Lapras go. What? See, don't say you didn't learn anything in physics, okay? Now you know the Lapras can move at 100 miles per hour when he gets scared. Okay. Oh, wait, did I do that right? Yeah, I did that right. Thanks for watching.